an hour-long lecture in my
Right. That
about 200 megabytes, but it's nice. It's on their permalink on their server that lasts for half a year, and then we can.
Okay, cool.
Yeah.
All right. So did it come up that it's recording to everybody? Did it give you a notification or no?
I didn't get one earlier.
I did. Okay. Actually, Alan, if I could ask you for a little favor, if you could also hit record just as like a backup.
I can't.
Oh, you can't. Yeah. Oh, really? You can.
You can give me permission. Sure.
Okay. Oh, okay. That's well. I don't think I can because I don't even have a settings button.
There should be a participants button at the bottom of your screen.
Yeah.
Is there a little tiny arrow button on the top of the screen, maybe?
Oh, okay. I could say. Make
oh, I've got the red light on the upper left that says recording, so you're definitely recording.
Okay. Okay. Well, I also made you a co-host, so if I can't figure something out.
Well, cool. I have a pause button. Okay.
Okay.
The first 10 minutes is recording. It's going to be so useful for everyone.
Now it's going to record the screen that I'm sharing, right?
Yes.
Okay. Cool. How do I do? All right. Let's do go on Windows. Okay. Cool. You guys got a nice view of my desktop, right?
Yep.
Yeah. Oh, cool. I can actually, if I look over, because I have two computers, I can see what I'm doing on the other one, which is kind of creepy. Okay, so the point of this tutorial is to get you familiar with OpenMM. So it's a Python library that allows you to do different molecular dynamic type stuff and PDB editing and topology editing. I'm not going to be able to go over everything because it's such a huge library. And I'm hoping what I'm going to go over is going to be useful for someone, but I can't guarantee that. But at least what I hope is that at the end of this, you'll see what kind of stuff that you can use this library for, and you'll have ideas of what or how you could work it in with your own research or not, if it's not useful. So if there's other stuff that you want me to go over, I'll happily go over it. So I'm just going to start with, if you go into Asana, there under the OpenMM tutorial, I uploaded a zip file yesterday. So this is going to have the Anaconda, the Jupyter notebook in it, as well as just the actual notebook saved as a Python script. So if you want to follow along, you can do it in Anaconda. Some of it I'm going to copy over, but a lot of it I'm going to kind of type out as we go, just kind of like how you're, it's kind of like if you had a math class and you're watching someone just put up slides of math in front of you. I don't know if you ever had that in calculus, but I could never follow along. But it was much easier when the person's writing it out and you're kind of writing your notes with it. So I'm hoping that will, if people want to follow along with that. But if you don't have the Jupyter notebook installed, you can just run the script as is, or you could even just open up an interactive Python terminal, and you can just do it that way too. So in this thing, there is the, oh, I moved it over. There's the notebook file, and that's the one that we're going to be using. So if you already have the Jupyter notebook installed, when you open it, it'll start like basically a terminal that sets up like a web browser. And it will broadcast it, and then hopefully it'll open up some sort of default web. Just for reference, I don't use Edge, it just opens up in Edge. But then you can go to wherever you saved your stuff, and you can open up the tutorial. As you can see on my new computer, I don't have a lot in my documents. My stuff I care about is games, tutorials, and Planned Parenthood donation things. So you can either open it up right there, or what I'm going to do is, because I have it opened up on another screen, is I'm going to type stuff out through there, and then we're going to do a whole new notebook, and we'll build it up one by one. So if you just go to New, Python 3, it'll open up a new notebook. Now, it'll create it with an untitled name. So you can give it a new name. I'll just call it Live Tutorial. And you can then choose, should save it wherever you were in that folder, or you could do save a copy or save as and move it somewhere else. In the meantime, If you just do a Google search for OpenMM and you go to their homepage, they have a very nice document section that will describe everything that works. There's a nice YouTube video by Peter Eastman from Stanford, who I believe is like the lead developer for this. But the thing that you'll probably be looking at the most is the user guide and the Python API. So with the user guide, there's 19 different sections. 1 through 7 is with Python. The rest of it's actually built in C++. You don't have to use C++. When you run Python, most of the time, it will call C++ code in the background. So what it's actually doing is calling C++ stuff whenever you run these functions in OpenMM. So you can look at the C++ stuff and you can code in C++ if you want. It'll be slightly faster than if you did it in Python, but I think Python's much more simpler, and you can just stick to those few sections. So let me just kind of give you, if you go to section 3.1, a first example. This is just kind of an overview of what OpenMM can do. So if you're familiar with Python, you've probably seen these import statements. SymTK is the main module that it includes. I never remember what these are. I just kind of copy it over and paste it. Another thing to note is if you haven't ever coded in Python before and you get a little lost, or you're like, God, there's no way I'd be able to remember all this stuff. Don't worry, I never do. I had 12 tabs of OpenMM docs open last night as I was finishing the tutorial anyway. I don't remember all this stuff in there, so that's perfectly fine. But the main chunk of it are these like 10-ish lines to set up a simulation. So if you had a PDB file, they include this in like an example folder in the install for OpenMM. You can load it in, save it as a PDB object. You can tell it what force field you want to use. There are built-in force fields. They have amber force fields. They have charm force fields. You can use GROMACS ones. I am not using the GROMACS ones in this tutorial because I would have had to copy over the entire GROMACS directory onto my local machine. But it's literally 2 lines that we will change to import a GRO file and use a GROMACS force field instead. But you can use the built-in ones. They have Amber 99 as well. You tell it, you give it the PDB topology that you just loaded in, what type of non-bonded method, hydrogen bond, stuff like that. You set what kind of integrator you have. So this is the temperature thermostat integrator. You set up the simulation with your PDB, whatever the system is that you just said, your integrator. You minimize the energy. You set what kind of files you want to output to. It will output to a PDB file. You can output it to other file formats. I haven't really looked at too many of those. You tell it to print out to the screen every 1,000 steps. You want it to say your potential energy and temperature, and then you run it. And you can literally run a whole simulation in 10 lines. Now, if you've done GROMACS stuff before, this is pretty much the same thing that you do in GROMACS. You import your PDB into PDB to GMX. You tell it what force field. You set it in your run.mgp file, what integrator you want to use. You tell it to export to an XTC and a TRR file, however often, and then you run it. So you can, and now in between all this is where you can change things, or you can change force field parameters, or you can obviously add solvent or stuff to it, or you can add additional forces that you couldn't do with GROMACS. So just as an overview, this is what you can basically do with a simulation. And I usually keep this open as I'm using it, just to keep in mind what the steps are. Where do I add the force field to the system, or do I add it to the simulation object? So it's good to just kind of have this thing open for reference too. So I'm going to move this over to here, to my other screen, because like I said, I keep it for reference. And I'm going to go back to my notebook, and we'll start with some of the things. And so what I'm going to do is I'm going to kind of follow the same thing that was in that little example, but we're going to add stuff in between. So all my, and actually I can keep it, you know, we'll just do it this way. So all my import statements, I just copy over from that example, and I just paste them in. So with Jupyter Notebooks, whenever you, this is kind of like an interactive Python type thing. Whatever you type in here, it will execute. If you just hit enter, it will do a new line. If you want to actually run the stuff that you put in, you press shift enter. So you hold shift and then hit enter. So it didn't output anything because all it did was import the modules. But if you did something like, let's do a little test here. A variable A equals 5, I'll do B equals 3. And if I were to then print A times B, and I do shift enter, it will then print it out there. Now, a little note is it will execute it in the order that you, not in the order that it's written, like a script. It will execute it in the order that you hit shift enter. So if I do in a new line, A equals 10, and I hit shift enter, and then I go back up to here, and let's say I changed some stuff and I got rid of A, and then I hit shift enter again, it will now print out a new number because it changed it over here when I entered A. So a thing to keep in mind is as you're changing stuff in Jupyter Notebooks, that if you make a change later in your document and you don't update it beforehand, it will use the most recent one that you put into the kernel. So if you want to run it in order instead, what you can do is then do whatever I set this equal to. You can leave that there. But if you go to kernel, you can hit restart, which will basically, it'll wipe the entire memory, and it will start it as if you had a new notebook. It won't erase stuff, but it will be like you never hit shift enter on anything. Or you could do restart and run all. And I'll probably end up doing that quite a few times during this tutorial, because if I make a syntax error, I'll probably have to re-enter something. And it's just the easiest way to do it. So we hit restart and run all. It'll ask you if you really want to do this, or if you say, no, I didn't want to do that. Just hit restart and run all cells, and then it'll really quickly execute them all again. So that's just a little example for that. All right, so in this little tutorial folder, there's also a file ac.pdb. Actually, I'm going to real quick just extract this to my desktop as if you guys were doing this. If you want to look at it in a text file, this is literally just an AC double-stranded duplex. So there's only 4 bases here, 120 atoms or so. So when we simulate it, it'll go really quick. So in order to, so that's the name of the file. The tutorial, move this file to wherever you have your Jupyter Notebook in. So if you want to check where that is, how do you check where this is? Oh, if you look at the URL, so notebook documents, and it's called live tutorial. So in this case, I want to move whatever this file is over to documents, and I'll just paste that in there. So this is where my notebook is, and this is where my file is. Then I can find the file in my notebook. You can give it the full path instead, but just be easier to have it in here. So we're gonna also, in Python, comments, like in Bash, begin with the hashtag or the pound symbol. So it's good just to keep an idea of what you're doing. So we're gonna import a PDB file. And to do that, we're gonna save it as a Python object. Now, Python objects can be numbers, they can be strings, they can be ints. These things, which we're gonna set equal to a PDB file, is just an object that holds all the PDB information. And I'm gonna go through what this stuff is stored in. Now, with Jupyter Notebooks, you can also hit tab to complete stuff. With mine, the arrow keys are a little finicky. So if I hit down, it does take a little while to update to go to the next one. It is actually there. It's just not highlighting it. But you can use your mouse and select whichever one you want. So if you hit tab, you hit PDB file. The argument that you give it is just ac.pdb. So this will import the PDB. And if I hit shift enter, it'll do it. Now, in order to get the positions out of it, what in order to access data within a Python object, you type the object and then a period. Now, if you hit tab, it'll give you all the stuff that you can access. There are positions, a topology, there are different functions, write file, get topology, get positions. These are basically the same thing. Positions is an actual array of data. Get positions is a function that will grab it for you. I don't know why they include both, but let's say you hit, oh, I want to do get positions, and you're not familiar with Python. If you hit Shift Enter, it'll give you bound method pdb.getPositions, and this looks like garbage. That's because what it is actually a function. And so in order to call it, you actually have to give it these parentheses. Normally there's stuff that's passed into it. This function doesn't take any arguments, so you don't pass anything in. And what it'll print out is all these different vectors of all your coordinates. So at the very least, now you know how to use OpenMM just to import a PDB file, and you can do any kind of edits to it.
Yes.
Yeah.
So the functions that you're using for PDB, those come from OpenMM, right?
Yes. So PDB is the object. It's created. Okay. Here's a way of looking at it. PDB file is a function that will create a PDB object, and you're going to store it as PDB. You can call it whatever you want, but I'm just calling it PDB. This object has its own functions, and one of the functions is get positions, and it will return the positions of it. So if I want to store it as something, I can say positions equal, and it will store whatever the result is. Now, if I hit Shift Enter, it's now stored as positions, and it won't print out the whole thing. I could then print them out if I want, or I could do whatever with it. But so it's a function that's in the object. This whole thing is called object-oriented programming. So you create objects. Those objects have variables, and then they have functions that you can do with those variables. This is an example of one of them.
So the PDB file function, it comes from the OpenMM app or OpenMM?
Yes.
Okay.
I'm not sure which one. So
which one, but one of them. Okay.
Yeah. So when you do
Yeah, you
import,
can comment it out. Yeah.
Yeah. So when you do import star, it will import everything within OpenMM app. It's the wildcard operator, just like you would have it, with Linux. I don't know which one it comes with. You'd have to just import one and see if it's there. But that's the beauty of hitting the tab, is that if you didn't import the right one and you try to tab it out and there's nothing there, you didn't import the right one.
So
yeah.
this might be like something that's not useful, but is there a way where you can print out all the information from PDB in a way that you can see it nicer?
Yes. So I'm going to show you that right now. So now that we saved positions, this positions is going to be an array of all the coordinates. So what it'll basically do is take these 3 columns and store them in the positions variable. So if I want to print out the first one, in order to print anything, you do print. Print is a function, for example, and then you give it whatever you want to print. And the argument is going to be positions, and let's give it the first one. So indexing starts with 0, not 1, kind of like with VMD, and then you can print out whatever this is. Now, I'll show you how to print out all of them in a sec, but I want to touch on what this actually means. OpenMM will actually use units with their data. Unlike when you code normally with Python, they're just numbers, and you have to remember that whatever number I imported is in a particular unit. So in a PDB file, whenever you code with this stuff, you have to remember that whatever coordinate I put here, this is by default in angstroms, and every program assumes that it's in angstroms. If you don't remember it's angstroms and you do math with it in Python, that's on you. OpenMM will actually import it with a unit associated with it, in this case with nanometers, and it will keep that unit with all the data. And if you multiply it by something or divide it by something that's in a different unit, it will actually do the unit conversion for you. So the first x coordinate is 3.0, 0.3429 angstroms, that's equivalent to 0.3429 nanometers. So it saved it as in units. This is what this import one does for unit, is it will import stuff with units. So if you want to get rid of the unit, as you're going along with it, I would advise against it, because it's very easy to make unit conversion mistakes, especially since some force fields use different units than others. You can literally just divide out by, in this case, nanometer. You can type out nano, and it will actually tab complete a bunch of units that we just imported. And then you'll see nano, like keep typing meter. There are nanometer and nanometers. It's the same thing. They just have two different aliases, however you tend to speak it. And then if you hit Shift Enter, now the unit went away. But we're going to keep the units in here. So just as an example, because I'm going to save this and I'll upload it with the final video anyway. Move units. I'm going to copy and paste that there and then divide by nanometer. And then it removes the unit. Now, if, for example, I were to, like I said, if I were to divide by, well, I'll get to that at the end when we change units. But if I want to convert it to a different unit, if I were to divide by, say, angstrom, now it will give me the value in angstroms. Or if I wanted to do positions 0, we will, let's set this equal to just P0 as a variable. And I'll hit Shift Enter. Now you can enter multiple things in one block, but when you, unless you hit Shift Enter, you can't tab out stuff. So now I can do P0 dot, and then if I hit tab, it'll give me a bunch of stuff I can do with it. If I didn't hit Shift Enter, none of this will come up because it didn't save it in the kernel. And it should have value in unit. And if I pass in angstrom, it will now do the same thing. It'll give it to me in the unit of angstroms. So you can do it as a nice way to convert stuff as well. Now, if I want to print out all of the positions, I already saved it into this object called positions. So I can just print it out in a for loop. I can type for, we'll say, we'll just call it pos in positions, colon, and if I hit enter, in Python, instead of breaking stuff up with curly brackets, everything is tab delimited, so it'll automatically give you a tab in Jupyter Notebooks. But if you're in a text editor, keep that in mind, you have to add a tab in order for it to say anything that is going to be in this for loop will have a tab after it. I can just do print position, I can hit Shift Enter, and now it'll print out all of my positions here. Now, you may notice something where some of these are exact decimals, or I guess finite decimals, and the other ones have like 12 to 16 digits of accuracy, and there's this one. It's just the way Python stores data. If you're just printing stuff out, there are ways to get rid of it, but there's nothing wrong with the value, even if it rounds it off. Let's see if I can, here we go, for an example, you know, 0.401999997. If you round it up, it's 0.402. And if you were to find this in the PDB file, it probably says 0.402. Just keep that in mind. It's just the way the data is stored. Simi, was this kind of like what you had in mind, or did you want it like put to like a file?
No, like that, because like when you were printing it out earlier, it was just difficult to see what was going on.
Okay, gotcha. Yeah, so I'm just printing stuff out like this just to see, so you can see what's in it. I mean, with any coding language, everything's stored in RAM, and you have to have like this mental vision of like what's being stored in these objects. So the nice thing about Jupyter Notebooks is you can literally just enter something and then say, well, how does this function work? What will it give me? Now it prints it out just like I'm doing a print function. So if this was in a script, you would actually have to put this inside a print function like I have up here in order to see it. But in the Jupyter Notebook, you can literally just enter what you want to see and it'll print it out as if it was in a print function for you. Okay, so this is how the topology, for how the PDB file works. So it's good in itself just to be able to see what type of, what coordinates and stuff are in the PDB file, but the rest of it is stored in the topology object. So we access that by PDB dot, we hit tab. So if you don't remember, heading tab's your best friend. We'll go to get topology. A common syntax you'll see with Python and most coding languages is anything that says get or set next to it is a function. They're called getters and setters. It's to prevent the user from changing data that they shouldn't within the object. So when you do get positions, it will return the positions to you. You don't go out and grab it yourself, because if you had access to that, you may change it when it's not supposed to. So it's always safer to use stuff like get positions rather than just accessing it yourself. So we'll do, oh, sorry, we're doing topology, not positions. So we'll do get topology. It's a function, and we'll set it equal to top. Now, if I do top, and I were to hit period and then tab, it will show me all the stuff that you can do with the topology. So you can get the number of atoms, get the number of bonds, you can get all the residues, you can get atoms, you can get stuff like this. And so I want to show you a little, do I have it saved here? I know I have it in PowerPoint. I just made this little thing to help you guys remember how this stuff is built in. So this is the structure of how they put the data into a PDB file. This would be the same thing as we imported a GROW file as well. It's the whole thing is stored in the topology. Within there, it breaks it down into chains, into residues, and into atoms and bonds. Now, you don't have to let's say you wanted to access a particular atom. You don't have to do it by saying, well, let me look in this chain, and within this chain, let me look at a residue. Within this residue, let me search for that atom. You can access the atoms directly from the topology. And so what it kind of means by these arrows is that you can go up and down this ladder or this pyramid however you want. I can access atoms from chains. I can access atoms from residues. I can say what chains, if I have this residue, what chain does it belong to? Or I could say if I have this residue, what bonds are in my residue? And you can access stuff like that. So the example that I have in here from the tutorial is we're going to list all the bonds that have a C2 labeled carbon in them. So here's how we would do it, is let's grab all the bonds. We'll type bonds equals top dot bonds. Now, this is something that you have to kind of search through the literature to find out what it is. When you do dot bonds, it's actually a function. And it's not just a function that returns a list, it actually returns what's called an iterable. For performance, they do it for performance reasons, because then you can just iterate over it without creating a list initially. And if you have thousands upon thousands of bonds, it probably would save you a couple seconds. I personally cannot stand it, so I always passed it over to a list, and this will create it as a list. So things like bonds, atoms, those I always convert into a list. And then we'll do a for loop and loop over all these. So we could say for, we'll say B in bonds. So it'll go through all the bonds and label them as B. And we're gonna extract the names. So I'll say names equals, and we'll make a list of these names. So B is my bond, and if I go over to my little PDB structure thing, this is what is contained in the bond. It has an index, an ID, a name. Actually, I don't know if it has a name, that may not be there, but it has atom 1 and atom 2. So these are the atoms in my bonds. So I'll say atom 1 if I want to grab the first one. and I want the name of it. So I'll do atom1.name. So what this is doing is I have this bond. I'm going to look at this atom. What about this atom? I want its name in that atom. And then I can do the same thing for the second one. B dot atom2.name. And so now I want to say, now that I have my names, if there is a C2 in my names, this is the nice thing about Python, is that you can actually just literally speak the way that the syntax is written. Then I will print the names. And now if I hit Shift Enter, it will now print all of the bond that have C2s in these. Now, if I want to know what the index is, I can then go back and say, well, I don't just want the names. I also want atom 1's index, and I also want atom 2's index. And I can hit Enter. And now it'll print along with the list, the names that I just stored into here, as well as whatever indices that these are made of. So this bond will be the 20th and 22nd. Actually, because they start at 0, it's technically the 21st and 23rd atom in my list. So if I actually go over to my PDB file and I look at my 20th or 21st will have C2, and then my 23rd atom will have N3, which is exactly what I have highlighted for. So these two are actually bonded in my topology. Does anyone have any questions about this little segment? Okay. So you can iterate through stuff like with, yeah.
Can you edit PDB files this way?
Yes. So
I would
well,
assume, like, you know, if you want to add and if you want to replace a hydrogen with a carbon or something like that.
yes, you can.
Right. Okay.
So there's a couple ways to do it. One way that you can actually look at this stuff, and this is a good point to bring it up, is the other part of this getting started part is the Python API. Now the website's a little finicky, but what you can do is you can search for stuff, and then you can look at all the functions that are in there. So let's say I wanted to edit the topology of it. I can type in topology. Now these are technically links. I found that usually these don't work. You actually have to click on something like topology.residues in order to take you to the thing. Because if I just type topology, it actually doesn't do anything. But now you can look at all this stuff that says like add atoms. So this one will add an atom to the topology. So you can give it the name. There's also an element object. You would pass it in whatever residue it is, and then you would give it an ID, which is an optional one. So you can add atoms to it.
What about you need the XYZ coordinates too, right? Somewhere? No?
Yeah, so yeah, you have the coordinates.
Okay.
Like if you wanted to change the coordinates for those.
Right. Like, you know, you add an atom, but then
Oh,
the add
okay.
atom thing. Yeah.
Yes. So
It wouldn't. Well, is it for the topology object or would it be for the PDB object?
So if you, okay, so let's keep topology open, and now let's do PDB file. You know what, let's just, because this thing is a little finicky. Oh, I can't access a new tab because I literally have this, oh, there we go. I had the screen sharing thing in the way. So as you can see here, I don't remember where everything is. So I have to type in stuff like PDB. See how some of the links are broken? Yeah, so this will only this will only read in
Read
the
it.
PDB.
Okay.
There is a thing called a modeler.
Okay. Yeah, I've used modeler. That's a Python-based.
Yeah.
Okay,
So,
yeah.
well, it's I don't know if it's the same thing that you're talking about, because this is within the SymTK module.
Right.
So this will add
Okay.
stuff like add solvent, add hydrogens. I
Mhm.
was going to go over this a little bit. I haven't figured out how to use it all, but there are ways to, so you can add, here you go, add topology, and then you can add in
Right. Okay.
positions that go with it. Yeah, so you could take your existing topology, for example, and then create a new topology for all the new atoms that you wanted to do and add it in here. And then what you can, at the end of it, is get the new topology of this thing. Now, if you just wanted to change positions, you can do that with the PDB object. So let's say I can literally do PDB.positions. Let's say access the 0th one. And I literally want to set it equal to, so let me just show what these look like first. Positions. So these are the first two, let me put these in print statements, because I think what it's doing is it's only showing the most recent one. So if I show these two, these are the first two positions. But I wanted to do PDB.positions 0. So notice how these are vector3 objects. You can just save it as a list. So if I want to just put it at the origin and I hit Shift Enter, it will say, oh, there's no unit. So instead I have to multiply it by a unit. Let's do it in nanometer. And now if I were to go back up to here and print it, now I've changed the positions of my thing. So keep that in mind, that if you were to then change that, if you're in the Jupyter notebook, if you then go back and re-enter code that used this, you already changed it beforehand. So you'd have to reload in your PDB. So this is a good point to show why this is useful. If I do go to kernel, restart and run all, it'll take a bit, it'll do everything that I just did, and then now it'll print out the new thing, and then it changed the positions. So you would probably want to make a copy of the object. Keep in mind with Python, most of their stuff is not copy by, it's called copy by reference. So if I were to say, I can access positions from pdb.positions, or I can access it from up here, I hit positions equal to this. Now when I hit equals get positions, it makes a copy. If I did, here, we'll just call it test equal pdb.positions. If I hit enter and I say now test 0 equals, and we'll set it equal to this thing, shift enter, and then I go back up to here and print it, it now changed this object. So it didn't actually copy the positions over to test. It actually made a reference to it. So now I don't have to access it by typing out pdb.positions, but then again, if I want to make copies of it, I have to do pdb.getPositions. So that's kind of the difference between the two. And some of this you kind of have to figure out by meddling with. There's also a module you can import called copy that will just do stuff like this for you. And that might even just be the easier way to do it.
Any reason they have, like, one has the vec3 suffix, the position 1, but 0 does not? Will that make a difference or no?
In position 1, okay, so this is saying vector3 is the object, and
Right.
it contains x, y, and z.
Oh yeah, that's true.
Yeah,
But like,
and then
on the
nanometers
top.
goes at the end, so the whole thing is that.
But when you change it, it shows it as a list and not a set.
When I change, oh, right here versus vec3 object. It really won't make a difference.
Oh,
You
okay.
can give it so if I do vec3 and I can give it, I think this is
Oh,
the
you can change the
syntax.
object. Okay.
And then if I were to go up to here, yeah,
Sure.
then it'll do that.
Mhm.
But most things if whatever you do with the PDB, when you give it to the system and you put it in the integrator and whatever, it will do it for you. So
Okay.
you can even give it a NumPy one. And actually, if you grab positions and you pass in NumPy equals true, it will actually save it as a NumPy array instead.
Mhm.
So it's very easy to convert. It will convert it for you. All right, so let me kind of show you what the next thing is. Once you have your PDB file, we can then we're going to grab the force field that we want to use. So we're going to set this equal to force field and this will be equal to, well, the object is called force field. And the parameter you give it is literally just the name of the XML file. So I'm going to just use the one that they have in the example, which is amber14-all.xml. Now, OpenMM uses XML files for force fields. GROMACS just use these arbitrary structured text files for force fields. You can import those as well. So if you go to your the user guide, and if I search for it here, using GROMACS files, you can literally give it a GRO file and a topology file, and where the GROMACS directory is that you want it to look within for all these force fields, and it will grab it there for you instead. And then you don't need to create a force field object. So you will need to create a topology file first, but all the parameters you don't need to put in. It'll find it for you. But if you just want to use the built-in ones, or you can even copy those over and just change it to accommodate for Allen's parameters if you wanted to use that. The second argument is the water model that you want to use. So if you don't know which ones that are in there, we go up to home, they should have, there's a lot of stuff to look in here. If you can't even find it, you can literally just do a search. Here we go. Yeah, so these are all the different water models that you can use for it. And then these are, so for Amber, I'm just gonna copy one over and put it in my water model. And so my second one is just going to be the file. Now these have to be in quotes so that they're strings. And now I have my force field object saved. Oh, cannot locate Amber. Oh, sorry, it's Amber 14. There we go. So also, little note is when you're in Jupyter Notebooks, let's say you do get an error, look at the thing at the very end. This will show you where what the code is that it's getting the error in. But if this is a little confusing, you don't need to look at it. You can literally just look at what the last thing is. All right, we'll change that to 14. Now with the force field object, there really isn't anything much to do with it, like with the PDB object. I'm gonna kind of skip over it. There's a couple things you can do. It's not really useful, like you can change some of the file names and stuff like that, but it's really just a temporary object used by Python in order to pass it into, or to use it to create the system. So once you have this, the next thing that we need to do is actually create our system object. So our system object is created from force field. So I'm going to call the object that I just made, tab it out, force field dot create. Oh, hit enter, shift enter. Yeah, some of it doesn't work that great with the tabs. But this should be the right syntax. So what you're going to pass in is the topology. So we'll grab it right from the PDB, just because I may have made some edits to the topology here that I may not want to keep those edits for. You then give it the non-bonded method. This stuff I'm literally just going to copy over just because it takes a while to type out. Copy and paste. So you give it the non-bonded method. I'm not going to give it a non-bonded method. You can also give it like particle mesh ewald, and then you can look in the documents to see what kind of ones that they have. I'm going to just do no cutoff. You give it the actual non-bonded cutoff. So non-bonded method is, this will be for long range interactions. It'll still cut it off at whatever cutoff distance that you give it. And then you can give it whatever constraint. So we're going to constrain all the H bonds. And, oh, it doesn't have create system. Why did this not work here? Oh, because I called it force filed. There we go. Now if I hit Shift Enter, okay, now it saves it. Okay, so now that I have my system, if I go back over to the example, your system is what's going to be passed over to your simulation object. Your simulation object is what does all the interesting stuff. But then you have, so the system is kind of this intermediary thing where you have to set up what the force field is and what the non-bonded stuff is. It seems a little tedious, but what's nice is that if you didn't say import a correct topology, you will find out here versus when you're already setting up your simulation. It'll tell you beforehand, something's wrong. So although there's kind of these intermediary objects you have to set up, you then pass it, you'll catch the errors first. Now we're already coming up on like 3 o'clock here. So a couple things that I had planned here was to show how to change some of the parameters or how to add a different force. Does that seem interesting to people, or do they want to see something specific?
Why don't you do whatever you think the most relevant example would be, because it'd be nice to see an example.
So the two I have set up is I can change, I can do like what Alan did with his force field, is just scale some of the parameters, and you can grab those and change those. Or I have one where we can add, now that would be relevant to me. I know Alan would want to see that, but I know stuff that like what Simi was doing with adding like different non-bonded forces, or I know Naomi was looking at adding constraints, and you can use that for this. So does anyone have any preference?
I mean, I'm not terribly constrained for time. Why don't we can just tell everyone that if they have to go,
Okay.
that's perfectly
I don't have a
fine,
preference.
but you can just record both if you don't mind.
Okay. Yeah, that's fine. Well, Greg, did you say something?
No, I said I don't have a preference, like whatever you.
Okay. I mean, they're both in the example file that I put on there anyway. So even if you don't get to them, but I'll go through them both anyway. So this one, I am just gonna kind of, most of this I'll just kind of copy and paste in just so that people can kind of see, that way you don't have to watch me type it all out. So for this one, we're going to change the parameters within our system. So once we've had our system that's created, this will now, so your system also holds all the forces and all the parameters that are in there. So when you create the system, it'll take your topology and say, okay, here are my bonds. I now have access to my force field. What are the bonded parameters in my force field? What are my angle parameters in my force field? So your system object is what contains all of that information. So the first thing that we need to do is we need to go through and find what forces are actually there. So let me just insert a cell above this and show you what I'm talking about. So if I go to let me shut my window. I don't know if you could hear the lawn work going on out there. If I do system.get forces, it will return all these OpenMM objects. Don't worry about what the syntax is. You have to use them directly, but it does tell you kind of what they are. So you have harmonic bond force, harmonic angle force, non-bonded forces. So this is your Coulomb and your Leonard-Jones, your torsions, and then there's a center of mass remover. So it centers your simulation throughout every step. So the first thing is we need to be able to say which one of these forces are we going to grab. So we need to, let's say we want to change, say the charges. Let's say instead of scaling all of the Leonard-Jones parameters, we had a funky world where the net charge was not an integer, it was half integer. So let's scale them all by a half or whatever. So we want to grab all the charges out of our non-bonded force. So first we need to find our non-bonded force by iterating over our get forces and iterating over the forces in our system. So in order to say that, we have to say, once we're going to go through all the forces, and then we'll say if this force is a non-bonded force. And that's what this is instance does. This is a built-in Python function. And you can even use this to say, is it a list? Is it a variable? But we're going to say, is it an instance of OpenMM non-bonded force? If it is, we're going to save it, and we're going to set it equal to whatever this force is, and then we'll break out of our loop. The break statement's really not needed because you're only looping over 5 different forces, but then it'll save it in this object, non-bonded force. So now if I wanted to do stuff with non-bonded force, I can say NB force, hit period tab, and this is all the stuff that you can get for it. So you can get the cutoff distance, for example. If I hit enter, it's 1 nanometer, just like we set it up here. I can add particles to it. I can get whatever the parameters were, get Leonard-Jones parameters, which is what we're going to use. So now we have access to the actual non-bonded force that contains all of the parameters. So what we need to do, I'm going to copy this part over, is we're then going to grab all these parameters. Now, in order to change them, what you have to do is you can't just, you can set particular particles parameters individually. But let's say we wanted to scale all of the charges, for example. We need to know what all of those charges are. So first we're going to make some empty lists for our sigma values, our epsilon values, and our charge values. We're then going to, we're also going to say number of particles. So how many particles are involved with this force? So if you had 2 different non-bonded forces, let's say you had a particular one just for oxygen and carbon, for example, it will only tell you how many particles are in that force if you had ones that were excluded from that. But this should return all of the parameters, or I'm sorry, the total number of atoms that we have anyway. So then what we're going to do is we'll make a for loop that'll loop over, we'll create an integer that loops over from 0 to, should be like 124, and then we will grab all the parameters. So let's store it in an object called params, and we'll get it from non-bonded force dot get particle parameters. And what you give it is the index of the parameters, or the index of the particle that you want the parameters for. So if I pass in 5, it will give me all the parameters involved in for that particular particle. So if I do print params, this will print out all of them, but it gives you out this list. The first one is the charge. So the value is this, the unit is this. The second one is the sigma value, and the third one is then the epsilon value. Now, if it has 0, some of these are 0, it just doesn't use a sigma and epsilon for those. So if epsilon's 0, it doesn't matter what else it's non-bonding with, it's going to be set equal to 0. But the nice thing is with these units is if you're used to looking at sigmas in, say, angstroms, and you're looking at some literature where it's in, the epsilons are actually in electron volts, such as in some of the old Mobcow papers, you can actually change the value in electron volts and it will convert it over to the right units for you. So each one of these params is now going to have this list. This is for the 0th one, the first one, and so on. Once I have the parameters, I then want to add them to my collections. So I'll do things like, let's keep this. So the first one is the charge. So I'll actually type charge dot append, and I'll add it to my list, params, and it's the first one in here. So I'm going to put in 0. If I wanted to add stuff for sigma and epsilon, I do something very similar. So it goes 0, 1, 2, which is the same thing as 1, 2, 3. So as I go through this list, I will then add all of these parameters to my list, and I'll have a collection of all my parameters. So this is also a good thing for if you wanted to come up with your own forces and just test energies. Now you don't have to grab all the parameters yourself going through the topology files. Say in GROMACS, you can literally import a PDB, set up this fake system, and then say, just give me all the parameters for these things. And then you can do whatever you want with these. So now that we have all the parameters, now let's go back through and set the parameters to be something a little bit different. Okay, so I'll copy this over from the file. So I'll make a loop that goes over, again, n particles. I'll do non-modded force dot set particle parameters. And so the first argument is whatever index of the particle it is. So the first, second, third particle, whatever. And then you give it all three parameters. Now, since I just appended it to here, or from params, they already have the units with them. So you don't have to worry about the units involved. And then let's say I want to scale these by, all my charges are now going to be scaled by 0.5. And so now this will set all of the charges to have a different, it will have half of the charge. Or actually, let's keep it more physically realistic. Let's say, I think Alan scaled this stuff by like 0.97. So let's scale all the sigma parameters by 0.97. So Alan, instead of putting your stuff in GROMACS, you could have just used OpenMM if they had it available then. Then you could go on and then say, well, what's the energies and stuff like that. So let's say we had this thing set up, and now we want to say, well, what was the potential energy beforehand, and what was the potential energy afterwards? Now, in order to do that, you have to create your simulation object. This is where it actually computes all of these forces. Your system object stores the forces, but doesn't tell you what to do with them. The simulation object then will take the system, and it will then do math with those forces. So we'll set it equal to simulation. The OpenMM object you call is simulation. Give it the topology, the system. So what forces am I using? And then what integrator? Now I didn't actually put the integrator in here yet. So I'm actually just gonna copy this over. And I'm just gonna use a simple relay integrator. And then you can give it whatever. So if you're just interested in the energy, give it whatever integrator you want. Doesn't really matter. So now that I have my simulation object, now if I want to get things like energies, let me remember how to do this. Here's how you would do it. So in order to do it, you have to grab a state of the system. So states are it's basically like a snapshot of what your system is doing in the meantime. I think Waleed said, okay, Waleed had to go. You said bye. So we want to take a little snapshot of our system. Now, before we can actually do that, what we need to do is, now that we set up our system, we never told it, we gave it the topology, but we didn't tell it where our positions are going to be. So we will say simulation.context. Context is what stores all of these states. And then we'll hit set positions. And then we'll give it just the initial PDB positions. Now, if I want to get the energy at a particular state, is a way you can think of it. We'll say state equals simulation.context. Most of the time when you do simulation, you're going to be accessing the context object. And then we'll hit get. Okay, so this is one that doesn't actually come up for some reason. But it's get state. And then within this thing, you can tell it all sorts of things that you want to grab from it. So actually, if you go over to the API and you do, actually, I think it's in this one. Yeah, so let me find where this would be. Here we go. So if you go to state, and you type that into like your little search thing, and you try to find a link that works. What you pass into it are all these optional parameters. Now, when you're looking at APIs for Python in general, but especially for OpenMM, when you see things as parameters to a function, and you see things, you have all these different options. Whenever you see something equals something, it's considered an optional argument. You don't have to give it everything. You give it what you want it to report. So if I want the energy, the potential energy, then I put in potential energy equals true. The value that is put in here for any API is always the default one. So by default, you're telling it, don't grab the potential energy. But if I want to grab it, then I type get energy or get potential energy and set that equal to true. Now, it doesn't matter for optional arguments what order that they're in. I can say kinetic energy equals something first and then potential energy. It doesn't matter which one that you're doing. So let's say get potential energy equals true. Oh, I think it's just get energy for the whole thing. There we go. I forget the syntax for get potential energy, but for the potential energy, but we'll do just get energy, and then I can print out this state dot get potential energy. And so now it prints out the initial energy. Now, if I wanted to do this again and then say, well, now that I've changed my parameters, does it change anything in my energy? And if you print it out again, so it actually printed it out in a weird way. The energy was different than what I had. That's because I already stored my stuff beforehand. So let me go to kernel, restart and rerun. And for some reason, my energy keeps going up. Let me see here. Let me just test something out. Okay, so for the sake of the tutorial, I will look up the syntax of how to do it. Unfortunately, you're gonna have to kind of just believe me that it will work in here. I forget where it is, where you actually have to update. Oh, here it is, hold on, I think I have it saved here. Oh, wrong one. Yeah, I'll have to, unfortunately, kind of get back to you guys and what the line is that will update the parameters for it. But this is essentially what you'd have to do to update the parameters for it. There's one other thing where you have to copy over and set, update the parameters in the context, and it will actually change the parameters. For some reason, it was working in my actual, if you look at the one that I gave as the example, it does give you different energies. For when we actually change the forces, I can't seem to get it to work with this one for some reason. So let me just put in, I'll just show you, I won't type it all out, but I'll just give the example for if you want to change the actual forces, if you wanted to add in different forces. So let's say we had we wanted to add in, so Lennard-Jones parameters are a induced dipole interaction. But if you wanted to go one more order in your multipole expansion, the next one would be R to the 8th. So let's say we had some sort of fictitious induced dipole. I guess that would be quadrupole induced dipole interactions that we cared about. And let's say we only cared about them for hydrogen and oxygen atoms. And we wanted an R to the 8th function. We can add in custom non-bonded forces. And you can literally just type out what the expression for the force is. So you would create this this custom non-bond force object, and the only parameter you give it is the expression for how you want to compute it. So let's say we had some parameter alpha to the 8th over R to the 8th. And this is just for scaling for units so that it actually worked. If I made it too big, the whole thing actually blew up. And let's say we wanted to have a combination rule where we had alpha 1 and alpha 2, kind of like you would with sigma 1 and sigma 2, and we wanted to do a geometric average over those. You would then set the non-bonded method to, the index is whatever type of non-bonded method. The first 0, I think, applies to the regular way that you would give like Coulomb and Leonard-Jones, where you have exclusions between 1,4 interactions and those are scaled. I think 1 doesn't use those. You'd have to look in the API to remember what the number is. I just always end up using 0. And then you tell it what parameters. So each particle in my system is going to have 1 parameter. It's going to be called alpha. Now, whatever you put here, it's actually going to fill in into whatever this is. So I'm going to say each particle has a parameter labeled alpha, and OpenMM will automatically look for anything in your expression that has this name followed by a 1 and followed by a 2, because it's a 2-particle interaction. And so it will take whatever the value is for particle 1, for particle 2, it will compute this expression, save it as this guy, and then it'll put it into here. So if I wanted to, I could actually just make this equal to X and make this equal to X, and it'll probably look a little bit better. So it will look for alpha 1, alpha 2, and then put it into here. So it's a similar syntax to, what was the thing that Naomi was using for her restraints? That library that Simi was trying to compile against. Simi, do you know what I'm talking about? If you're still here.
I think Simi left.
Alan, I don't know if you know what I'm talking about.
It was on the tip of my tongue, but yeah.
Yeah, sure, that Trieste thing, the thing the Italian people did.
Yeah, the one where they were like, yeah, you know, Alan, I put all this stuff into this thing, whatever it's called.
Plumed.
Plumed, yes, Plumed. So if you, this is very similar to adding different stuff to Plumed, where you just give it the actual expression and then the variable. And so you can do things where, let's say I only want it between hydrogen and oxygen bonds. I can loop through all of my atoms, and I can say, well, this atom it has an element object. That element, if the symbol is H, then I want to add it to my list of hydrogen atoms, and then I'm going to add a particle parameter, and this is the value of that parameter that I pass over. So it would be 0.1 nanometers. That is an alpha value of 0.1 nanometers. Or if the element is oxygen, add it to my oxygen list, and then add a particle parameter for oxygen. Else, add a parameter to 0. So the pain in the ass part about non-bonded forces is you have to add a parameter for every single force, even if you don't have the force, and it will not compute the force if you don't tell it, if you tell it not to, but it still needs a parameter. By default, it's designed to work for all particles interact with all particles. We are going to be using particle groups where it will only interact between hydrogen and oxygen atoms. It won't actually compute it, but you still have to loop over every single particle and give it a parameter. It will return an error otherwise. The other thing is you have to give it the same exclusions. You can tell it to use no exclusions, but I'm going to say, look, take the same exclusions from my non-bonded force that I found up here, get exclusion parameters. So it's kind of similar to get particle parameters. And this is for like 1,4 interactions, where the Coulomb interaction for amber is scaled by like 0.83 and Leonard-Jones is scaled by like 0.5. So it'll take, so this will return what particles, particle 1 and particle 2. It'll return Q1 times Q2 times that scaling factor, and similarly for epsilon. And so all I'm going to do is loop over all these exceptions and then say for my custom force, use the same exception. So now that I have my parameters added, I have my exceptions added, I then will create an interaction group. And so what this will do is say anything in my first list will interact with everything else in my second list. So all hydrogens will interact with oxygens. this will not have all hydrogens interact within themselves like a traditional non-bonded force would be. The example they give in the tutorials is like if you had solvent and solute interactions, you would give one list as one and the other one as the solvent, the other one as the solvent. And so it would only have hydrogen interacting with oxygen. You then add it to your system. Now, if you look in the actual never mind. So this is how you would then add an additional force. You can also remove forces if you wanted to. So if I wanted to do let's say I wanted to just test out what the energy would be for just this interaction, but I didn't want to code up everything, but I only want to look at that energy, say as I'm moving something apart from another, I can remove every single force and then add this force in, and it'll only compute this force. So for things like what Simi was looking at for hydrogen bond interactions, if we wanted to just look at what the energy difference would be just for that interaction, you can't ask OpenMM to get the potential energy for a particular interaction. You can do it for the system together, but the way around that is to say, well, my whole system only has one force. And so if I say get the energy for the entire system, you're only getting the energy for that one force. So then you can also remove forces and remove the other ones. Or if you wanted to replace, let's say we had, so the non-bonded interactions in a simulation, when you add them in there, it can be very costly. So if you wanted to have, say, instead of point charges, we had softer densities where they act as point charges at far distance, but as they get closer, there's actually an overlap. This is something that I'm working on. And we actually want to shrink down the Coulomb interaction because of that overlap in density. What I don't want to do is add in one force and then throughout my simulation, compute a second force that also uses the position. It'll actually double the amount of computation power that you need. So what you can do is you would remove the non-bonded force and then change the actual expression to have that additional term. And the computational power will be about the same. So when you do simulate it, keep that in mind. The more forces you add, the more expensive the calculations are. And if they all use something like distances, this is where most of your, I would say half of your CPU resources go to, is calculating distances between particles. If you have two forces that calculate distances, add in one force, but then add in different particle interaction groups with different parameters if you want to group them that way. That way it's the most efficient way. And they actually say something like that in the tutorials as well. Okay, so let me, I didn't call it topple, I called it top instead. There we go. So now it works. And the thing that I'll return is how many forces that you have total in your system now. So now I have 5 total forces. So if I ran it again, I'm not gonna, if you hit Shift Enter again, it'll actually go up to 6. You're adding the force twice, but now you have 6 total forces. Okay, so now let's actually, if I want to, let's minimize the energy of my system. So now I have all my forces set up. I've changed all my parameters. Now let's actually run some sort of simulation. First, let me see what my initial energy is. So I'm just gonna create another state, tell it get my energy, and print out the initial kinetic energy. Now, if I then do minimize my energy, the thing that bugs me about this is it won't actually give you any kind of updates, and I haven't figured out how to tell you how to update it during an energy minimization. It kind of just does it in the background, and you have to just assume that it's running. So when you hit Shift Enter, it won't actually give you anything new, which may be a little problematic if you have some large simulations. I know in GROMACS it'll print out a step of like what step you're at, what the total energy is, what the maximum force is, and stuff like that. There probably is a way, I just haven't found it. So now if I say, well, what's my new potential energy after minimizing it? Well, it's at a lower potential energy. So I did actually reach a different lower minimum. And you can give in parameters like what the maximum force is or what the smallest change in energy is, just like you would in GROMACS. But the default values seem to work fairly well. Keep in mind, I didn't add solvent for this. You can add solvent. I'm not good with adding solvent with simulations. I don't deal with solvent stuff. You would do it through the modeler that I showed you. I tried it once. It's literally as simple as like modeler dot add solvent. And if you gave it a water model, it adds it to the PDB file like that. It's like adding waters in GROMACS. Or do it on GROMACS, save your topology in GRO file, and then import it through here. That's personally what I would do.
Chris, can you give it two topology files at the same, I mean, two different topology files when you have two different molecules, like the same way we add different line of topology in tuple.top.
Okay, so you know how when you create a topology file in GROMACS, it'll have those include statements.
Yeah.
Yes. If you give it, so when here, so using GROMACS files, if you give it this directory, it will go through all the include statements. So when it looks into this directory, it will find the force field file. And that one has usually 3 lines: include non-bonded, and it'll give you the file, include bonded file, and then blah, blah, blah. So it will actually go through all the include ones, just like you have in yours. So as long as those files are in the same directory that you're running in, or you give it the path for it, it will still go through those include files.
Okay. We don't need to specify their names in the code.
No. So you would give it the one file.
Okay,
So
got it. Yes.
Yeah, you would give it that topology file. And if this topology file also has include statements, then those are all going to be relative paths. So as long as those paths are correct relative to where you're running your script, then yes, it'll work just like GROMACS would.
Okay, got it. Okay.
I don't know if there's a way to mix them with the built-in ones, but I think most people are going to find it more useful to just literally import the GRO file and the topology file that you do with GROMACS and do it that way. Okay, so 2 parts are left. First thing is reporters. These are a couple quick lines. So now we're going to run our simulation. We'll do it for, say, 10,000 steps. And every 100 steps, I want to save it as a PDB. So they have built in a PDB reporter that will save the outputted coordinates to a PDB file. Now, GROMACS will use XTC and TRR. You can't use those exact formats. There is a compressed, the XTC is a compressed format, and it helps you save disk space. There is a way to use a compressed format in GROMACS. I'm not sure, I've never used it before, or I'm sorry, to use a compressed format in OpenMM. I haven't used it before. It is there. But for starting out, the simplest thing is just to use exported to PDB. But
I think there is a function called the MD trash thing Python has. I think for
there is. Okay.
I think maybe.
What I do know is if you, I think it's in this one. Let me see here. Oh, what am I doing here? There is a way to, make custom reporters. Best thing about so I can't, it's somewhere is in this one. It may be in one of the more advanced things. So if you back out and you go to, so if you hit something like with 8, it will give you everything else. These are like more advanced topics. Where is it? I know I found it from just a Google search before. But what you can do is you can make a custom reporter that will, so what this will do is it will call the PDB reporter every 100 steps. You can say, I want to use my own reporter. And you would create the function and you would give it that one instead. And what you can do is output it to a PDB file and then compress it. Or import that other what was that library that you said, Parisa? Whatever it's called. ND-Traj, yeah. So if there is one in Python, you can do it to where you make your own function that will call that library and export it. And you would design it so that the simulation variable will give you the positions, and then you can just save your own file. But the built-in and easiest one is just the PDB reporter. I'm sorry that I don't remember where to find all this stuff. As you can see, there's a lot of stuff that's in this library, and I've only touched on the tip of it. The last thing is having it print out stuff as you go along. So every 1,000 steps, I want it to tell me what step am I at, how much simulation time, what's my kinetic energy, what's my current potential energy, and then this last thing is a separator. I always add this because the default separator doesn't put a space in between it, and it's kind of hard to read it. Your eyes may be better than mine. So this will just create the reporters, and then when you want to run it, it's as simple as simulation.step take 100,000 or 10,000 steps. Hit Shift Enter, it will run it. Every 1,000 steps, it printed out exactly what I said, the time in picoseconds, the current potential energy, the current kinetic energy. As you can see, I gave it a relay integrator. I didn't give it I didn't give it any initial velocities. If you give it the length of an integrator, it will generate the velocities according to the right distribution. I didn't do that, so this is like starting from nothing. And then it'll print everything out into, I don't know why I called it energy min.pdb. I could actually just call this progress.pdb, and then I'll output it to there. So let me rerun this. Now, as you see, I typed it in again. And so what happened is it picked it back up after those first 10,000 steps. So stuff like what I'm doing with my work is, let's say I wanted 10,000 steps, and I want to do something every single step. For example, change charges. I would do simulation.step. I would just have it step once, and then I would say, call whatever my fluctuating charge model is. It will update my charges. I would give it stuff like simulation.context. It can access all the parameters. It will update them then, and it'll go through this for loop and update it one step at a time. So you can do stuff for in between, or if every few thousand steps you wanted to change a parameter, you could probably do that. Now, there isn't a way to do replica exchange, unfortunately, but if someone was adventurous enough, they could probably code up their own Python version of it if they really wanted to use OpenMM for it. And then you can do that every so many steps and run your own function and say, do these energy things overlap or whatever. But you could do it by just saying how many steps that you wanted to do. So that's, the only other thing I wanted to show is if, do I have this here? Let me see here. If you wanted to do like custom integrators, here's an example of something that you can do too. So instead of using like a relay integrator, it works kind of the same way you do with the custom non-bonded forces, is you would literally tell it how you want to update stuff. So you need at least two, X and V, for position and velocities. And the way this works is to say, the first parameter is, what am I updating? So if I put in quote X end quote, I'm saying update my positions. And I'm gonna say, update it according to this way. It's gonna be X, this will be equivalent to X equals X plus VT. And then if I wanted to do, I would then have to say what my update for velocity is. And let's say I didn't want to change my velocity. So if I just wanted to start with initial position and say, pull something apart from each other at a constant rate, I would do it this way, where my velocity doesn't actually change. And I just set it equal to, say, half an angstrom per picosecond. And then what I can do is set it so that my speed is always at this speed. This guy is held fixed, and I just pull this apart. And so you can use a custom integrator just to put those things apart. And then every single step, what you could do is go through something like let's say I did 10 steps, I would do simulation dot step, I would step once, and then I would then grab my state and print out my potential energy. And then every single step for every single pole, I get my new potential energy. And you can do stuff like that. So yeah, that's kind of most that I had planned for this. Anyone have any? I know it's went kind of late. Sorry about that.
That's okay. If you don't mind, I'm going to stop the recording. Is that good?
Yeah, that's fine.
Yeah, I'm going to stop recording now.